Hi, Assalamualaikum and good morning to Dr. Ibrahim and all my classmates. Today we are from group 3 are going to present our interesting D-block transition metal coordination compound, which is a TRANS-DICHLORIDOTETRAKIS imidazole cobalt trichloride. Okay, this is our group members, which are me, Aida Zafierah, SYUHADA, HAZEL, SITI BALQIS and NURFARHA NATASHA. The title of our journal is Synthesis and Characterization of TRANS-DICHLORIDOTETRAKIS imidazole cobalt trichloride, a new cobalt-3 coordination complex with potential product properties. There are 6 writers of this journal that was published on 3rd September 2018. Next, I will pass to the next presenter.
Okay, so I will continue with synthesis of TRANS-DICHLORIDOTETRAKIS imidazole cobalt trichloride. Okay, first step is in a 50 ml round bottom flask of 0.1 gram of 0.21 millimole of 1 was partially solubilized in 10 ml of methyl isobutyl ketose with stirring and slightly heating at the temperature of 40 Celsius. In because 0.071 gram of 1.0 millimole of imidazole was fully solubilized in 20 ml of methyl isobutyl ketose with stirring. The solubilized imidazole was added to the 50 ml round bottom flask. The initial solution is light green with green particles visible in the solution. A water condenser was attached and the solution was refluxed at 115 degrees Celsius for 2 hours. During the reflux, the starting material became fully solubilized. After the reflux period, a new green solid in blue solution is observed in the round bottom flask. The solid was collected on a medium filter fluid and washed 3 times with 5 ml portion of ice-cooled methyl isobutyl ketone, followed by 3 times of 5 ml portion of ice-cooled diethyl ether. And then last, the yield is 0.07 gram of 77.5% yield. So next, we'll continue to Aida.
Next, I will continue with point group determination. This is the molecular structure for the TRANS-DICHLORIDOTETRAKIS imidazole cobalt trichloride. If you can look at this complex compound, this compound contains 2 types of ligands, which is the first one is chloride ion, which is in the green color, and the second one is nitrogen donor atom of imidazole in the pink color, and the central metal ion is cobalt-3 ion. This compound have 6 coordination compounds because the central metal ion is surrounded with 6 ligands. So the geometry of this compound is the octahedral. The first step to determine the point group is we need to know each symmetry operation of this complex. The first symmetry operation is E, 2 C4 principal axis, 4 C2 axis that perpendicular to C4 axis, 2 sigma V planes that containing C2 axis, 1 sigma H, 2 sigma D planes and 2 improper rotation S4, and lastly is I, which is the inversion. The high symmetry point group is the point group D4H. It is determined by using the flow chart of the point group. Next, pass to Hazel.
Thank you, Aida. So now I'm going to explain about types of ligand bonded to the central metal based on crystal field theory and also ligand field theory. Okay, next slide. So based on the diagram shown here, we can see that the coordination number of cobalt central metal is 6, and there are 6 ligands surrounding the cobalt central metal. So the molecular geometry of this complex will be octahedral. And there are also 2 types of ligand attached to the central metal, which is the chlorine and nitrogen donor atom of imidazole. So the chlorine atom will act as a weak field ligand, whereas the imidazole will act as strong field ligand, based on the reference to the spectrochemical series. However, both of these ligands will act as monodentate ligand because there is only 1 attachment from each nitrogen donor atom of imidazole and chlorine atom to the cobalt-3 central metal, and each ligand will form local sigma symmetry with respect to the metal ligand axis. And since the geometry of this complex is octahedral, so splitting of d orbitals into T2G and EG sets can be observed. And of energy level between these two sets is denoted by delta O. Delta of this complex is assumed to be high because there are a greater number of imidazole, which is the strong field ligand present, and cobalt-3 central metal will adopt low spin configuration, which is T2G6 EG0. That is the explanation based on the d orbital splitting under the octahedral field. The dx square minus y square and dz square orbitals from EG set will occupy in higher energy level, which is unfavorable, as their orbital lobes lie toward the negative point charge or ligands. Thus, they will have more electrostatic repulsion between the electron of ligands and also central metal d orbital, and it will cause destabilization of orbitals. Whereas the dxy, dxz, and dyz orbitals from T2G set will occupy in lower energy level, which is more favorable, as their orbitals lie between the negative point charge, and hence they will have lesser electrostatic interaction, and the orbitals are stabilized. Next is the ligand field theory aspect. So the chlorine ligand will act as a pi donor ligand. The electron from ligand pi orbitals will occupy the bonding combination, and the original electron from d orbital of cobalt-3 central metal will occupy the anti-bonding T2G orbital. So the net effect will be the previous non-bonding T2G orbital will become the anti-bonding, and it will raise to a closer energy to the anti-bonding EG orbital. So the delta O is decreased. Whereas for imidazole ligand, it will act as pi acceptor ligand, and the vacant anti-bonding orbital on the ligand, which is the LUMO, will be located at higher energy compared to the metal d orbital. So it will form bonding T2G combination with slightly lower energy compared to metal d orbital. So the net effect is the homo-LUMO separation between the bonding T2G and anti-bonding EG set is increased. So the delta O increase.
Okay, next I will present about the IR spectrum of the TRANS-DICHLORIDOTETRAKIS imidazole cobalt-3 chloride. Okay, if you guys look at this spectrum, it will be 7 possible main spectrum that related to the main functional group present, which is the first one is a cobalt nitrogen stretching that appears as a weak peak around 500 to 700 centimeter -1. And then the sharp and also the strong peak for the second spectrum, which is around 950 to 1050 centimeter -1 is belong to the cobalt chloride bond. Next, the NH bending have absorption peak around 1600 to 1690 centimeter -1, while NH stretching appears around 3100 to 3300 centimeter -1. Since it is the secondary amine, so it shows the weak peak and have one band. Then the peak at 1700 centimeter -1 is indicate that the C double bond C is present. And then finally, I found on the internet that absorption value for the IR spectrum for the imidazole molecule is around 2400 to 2800 centimeter -1. This value appears in the spectrum as a medium intensity peak. Then Hazel, we continue with the UVV spectrum.
Okay, so for the UVV spectrum for this complex, the figure 3 here will indicate the UVV absorption spectra of 2 millimoles of trans cobalt-3 complex in water when the time is 0 and after 36 hours, which will be represented by the black lines and red line respectively, and also addition of 20 millimoles of ascorbic acid into the complex when the time is 0 and after 36 hours also later. So the UVV spectrum of cobalt-3 complex in water, which can be represented by the black line, will display two maxima peak at 390 and 520 nanometer respectively. So at 390 nanometer, the observed DD transition will be singlet A1G to singlet EG. Whereas for 520 nanometer, the observed DD transition will be singlet A1G to singlet A2G. However, after addition of 10 equivalents of ascorbic acid, which is represented by the blue line when the time is equal to 0, the intensity of DD transition of cobalt complex will decrease over the time. And the green line will represent the addition of the ascorbic acid after 36 hours. So it can suggested that the reduction of cobalt-3 central metal is observed. Okay, next I will pass to Anor to talk about magnetic properties.
So I will present about the magnetic properties for this compound. So our compound is TRANS-DICHLORIDOTETRAKIS IMIDAZOLE cobalt trichloride. So as Aida said earlier that our compound is occupied the coordination number of 6. So the molecular orbital for this compound will be octahedral. So the end configuration for our transition metal in this compound, which is a cobalt 3+, is D6, and there's a 2 type of ligand, which is chlorine and imidazole in this compound. So chlorine is a weak field ligand, meanwhile for the imidazole it have a strong field ligand. Since there is of the ligand imidazole is greater than chlorine imidazole, so the compound will be a low spin compound since the imidazole is strong field ligand. So next, this is the molecular orbital energy, the octahedral, molecular octahedral. There will be a T2G set and EG set. Since our compound is low spin compound, so the electron will fill the T2G set first, continue to EG set because the splitting energy for the orbital will be higher. So as you can see in this diagram, there is no unpaired electron. So this compound will be diamagnetic compound. Automatically, the spin moment for this compound is 0. So next, I will explain about the stereochemistry or geometry of metal complex. So what is stereochemistry? Stereochemistry is a study of relative spatial arrangement of atoms in space. There's a 2 types of stereoisomer, which is the first one is geometrical isomer, which the compound that have a same connectivity but a different arrangement. Meanwhile, for the optical isomer is non-superimposable mirror image. So in this compound, I see that there is no optical isomer observed in cobalt-3 complex, as there is a presence of a mirror plane length between the central metal and ligand. But there is a 2 geometric isomer, which is cis and trans can be formed. So first, I will show you the trans isomer. So our focus complex. The chlorine and imidazole lie in their opposite side respectively. You can see it clearly in side view, which is the chlorine in the green one in the opposite side, and the imidazole in different side. So now this is the video from the side view. And next for the cis other geometric isomer form, which is cis isomer, the chlorine and imidazole ligand lie in their same side respectively. For the top view, you can see the chlorine ligand is on the top of the compound. Same goes with the side view, you can see it clearly. So this is some of the video for the cis isomer. So next, I will pass to Tasha for the application.
So now I'm going to continue with the advantages of our complex and also the application in the anti-cancer therapeutics. So I'm going to discuss about the advantages first. So for cobalt-3 complex, it is a good alternative as easily available. It's also low cost, much more cheaper than ruthenium, which can cost $262 US, and it's less toxic compared to the platinum complex, which is cisplatin used in treating cancer. So for the applications in the anti-cancer therapeutics, it is an effective pro-drug capability. It exhibits octahedral and low-spin D6 configuration. And how does pro-drug works? It remains inactive until it reaches disease cells, at which time it becomes activated and cytotoxic. And it's kinetically inert complex, cationic complex. From the previous studies, it indicates that oxidation state of +1 and also +2 octahedral cobalt-3 chaperone complexes can penetrate hypotoxic regions of tumor models and cancerous cells. And last but not least, it's functional cobalt complex pro-drug capable of displacing ligands due to its solubility in polar solvent. In HNMR, in deuterium oxide suggests lability of chlorine and imidazole, ligands display favorable characteristic in desired or vivo application. I mean, that's all from our group. Thank you.